Today, we are presenting our research on memory-augmented RAG for lifelong autonomous driving, enabling continual adaptation to long-tail scenarios. This is a final project for CSE475, and our team members are Linda Chen, Aryan Kaluskar, Alexander Matter, and Shaikh Pasha. So autonomous driving models perform often well on common occurrence scenarios such as good weather, city streets, and highways, but they struggle often on facing rare or completely unseen scenarios like construction work with unexpected road markings, extreme weather conditions causing poor visibility, and even vehicle crashes. So this research paper that we analyzed memory-based neural networks for end-to-end autonomous driving investigated the use of memory-based and memoryless models to compare their performance on simulated test circuits. PilotNet is a memoryless approach which processes one image frame at a time with 17 million parameters, and it still cannot understand motion or predict behavior in state-dependent situations like approaching curves, sudden obstacles, or even lane changes. While MEM-DCCP, the memory-based baseline, processes sequences of 3 image frames and uses temporal memory, and it learns spatiotemporal dependencies, allowing the model to understand motion, patterns, trajectory, and context with only 910K parameters. And so the results that the researchers found was that the memory-based models like MEM-DCCP dramatically outperform memoryless models. When evaluated on unseen track variations, camera misalignment, or heavy sensor noise, PilotNet fails most tests and was only able to complete 3 out of the 6 variations in breaking down whenever conditions change. While MEM-DCCP completes 5 out of 6, handles camera shifts, and even works with significant noise because its temporal memory lets it filter out the bad frames. Overall, DCCP adapts to real-world variation exactly what's needed for robust autonomous driving.
Alrighty, our MEM-DCCP baseline is solid, but like pretty much every model out there, it really struggles to generalize when it's hit totally new road. You can see here that there's a huge generalization gap. The error rate is nice and low on our training circuits, but as soon as the model encounters unseen circuits in our test set, the error just spikes. So the main goal of our project was to figure out a smart way to close this gap. You can go to the next slide. So that challenge led us to our main question, which was, can retrieval augmented generation, RAG, actually improve how well autonomous driving models generalize on brand new circuits? So first, let's quickly cover what RAG is. It's a technique that started in AI language models. You can kind of think of it as giving the AI a smart search engine. Instead of just relying on its internal memory, it can quickly look up external information like a database right before it gives you an answer. So we've adapted this idea for the car. We're essentially giving the car the ability to look back at its successful past driving experiences to inform the current unfamiliar decision. So our hunch was that this immediate memory lookup capability would be the key to closing that generalization gap. Next slide, please. So the diagram shows our proposed framework. The RAG system is super efficient, low-cost wrapper that sits right around the existing MEM-DCCP model, and it needs no retraining or fine-tuning of the original network. So it works by following a quick 3-step process during the drive. So step 1 is to predict, and this is where the base model takes the current image sequence and gives us an initial base prediction for steering and speed. Step 2 is to retrieve, where we query our massive memory bank, a static vector database of all our training scenarios to quickly find the top 5 past scenarios that took the most similar, or top 5 past scenarios that look the most similar to the current one. And then step 3 is to augment, and we blend the base prediction with the memory targets to produce a highly accurate final command. You can go to the next slide. Thank you. So let's look closer at the retrieval and augmentation details. The RAG system is designed to retrieve those past experiences from a pre-computed vector database to improve predictions at test time. So for the actual lookup, we used FAISS index flat IP to find the similar driving scenarios in the database. So this is critical for performance. We chose this because it allows us to compute the retrieval process in under 10 milliseconds, which is fast enough for real-time driving scenarios. And then finally, we weighted averaging model. Finally, the weighted averaging combines the model's learned patterns, which we weight at 70%, with the retrieve control commands, which we weight at 30%. And this balance allows the system to rely mostly on the trained network, but use the memory from similar past situations to make that final correction.
All right, so for our data set, we use the Formula 1 follow line data set, a sequence of images as the inputs, and some control labels as the outputs. The training set is used to populate the RAG memory, and the test set is only used for the evaluation. And the data set was created by an explicitly programmed PID controller that navigated circuits by following a red line centered on the road. And you can think of the outputs as the V speed and steering values. Next slide, please. we split our data set into some training and testing circuits. The training set includes tracks like the extended simple, many curve circuits, Monaco, and the Nürburgring. And these are only used to populate the RAG memory. The test set consists of the simple circuit, Montreal, and others, and these have more complex geometries, and they make for good tests. Next slide, please. So for our baseline, we use the MEMDCCP model that predicts driving commands from visual input. To incorporate the retrieval, we added RAG as a wrapper, the top K most similar past scenarios from memory, and the final command imputed by combining the base prediction with the retrieved outputs. And this allows, all right, yeah, see it now. All right, so each in our data set is performance using the mean absolute error between the predicted and true control commands. And in order to understand the challenging conditions, we divide the results into normal and difficult scenarios are defined by the sharpest turns in the data set. And this is where steering accuracy matters. And yeah, I'm done.
Yeah, so I can go for, we also did hyperparameter tuning. We tested a few K values and alpha values to find that K equal to 5 and alpha equal to 0.3 was the best setting. And that gave us the results on the next slide. As you can see, RAG has significantly outperformed our baseline, MAE. So MAE is mean absolute error that we were calculating between the angular velocity and the linear velocity that was given in the data set. And what we are seeing is angular velocity is improving significantly because it depends on like the steering angle, and steering is far more context dependent than like straight speed, like linear velocity. So that is why having more scenarios from the past, which RAG enables us to do, improves the angular velocity MAE. Other than that, angular velocity is also very sensitive to geometry. Like there are some curves that are very different from other curves. So that is why having a RAG on the previous successful training data set helps a lot. And yeah, so on the next slide. So like I was saying, the strength is we have a really good improvement over the baseline MEE, about 21% overall. And this is significant because we didn't have to do any retraining. This was very computationally inexpensive, but there are also weaknesses like even though it is optimized, the inference latency is a problem in real-time driving scenarios. Other than that, there could be scenario storage overhead where we have to store all of these scenarios in a database to fetch it at a later point. And I think most importantly, there is a bit of sensitivity to retrieval quality that we need a good retrieval model and a good embedding model to improve the performance of this RAG system. So yeah, on the next slide. So we conclude that the retrieval augmented generation system can enhance the capabilities of this end-to-end driving model because we have multiple scenarios being retrieved. This sort of reduces the variance while driving because it gives more context to the driving model. And alongside its own base training, this is able to supplement that training information and make better predictions. Other than that, angular velocity was the most effective I guess, help from RAG, where we reduced the MAE by over 34%. And like I was saying, the most effective configuration was 3 equal to 5 for the KNN that we use for RAG. And instead of constantly having to retrain the models, we can deploy systems in the real world using RAG that can leverage all of the training data set as a RAG memory as well, which is pretty analogous to the human driving because even when we encounter roads, we sort of go by memory. And instead of driving on the road as practice, we are able to drive on it directly using memory. So on the next slide, we also have a bit of future work that could go here, something like hierarchical memory, where there could be different nodes that could be for different purposes. Like one node could be for highways, one node could be for neighborhood roads. Stuff like that would increase the specificity and also increase the speed because the model only has to look in a subset of the environments. And other than that, this could also enable real world and real-time support for continual learning because it's like if you have 10 vehicles out there, all of them could be feeding into this RAG memory and all of them could be learning from each other's experiences. That would make the system very powerful at a massive scale. So yeah, thank you for this opportunity and we would love to hear from you and we hope that you like the project. Thank you. And yeah, we also have references from the papers that we have read and collected.